Okay, hey, let's look at 7.2. We're in a new chapter, and this one will have a lot of integration techniques that we're going to pick up. A couple of them you will be familiar with, such as U-sub, and that is what we're working on today. So just a nice refresher on U-sub and also just regular integration. So this first one is talking about if f, capital F, is a function such that the derivative of capital F gives us little f. So we can see the relationship between big F and little f. Then if I say I want to take the antiderivative of little f, it'll come out to give me the original function big F. Because remember that this really was the derivative of big F. So if I take the antiderivative of the derivative, it's going to give me the original function. And then don't forget, if it's an indefinite integral, meaning there are no bounds declared, then we add the plus c to account for any constant that could have been present in the original problem. So this one is just a nice straightforward basic integration. Remember the power rule where we, oops, I might have covered up the power rule. Or not, I guess it's not there. Let's just go ahead and use the power rule though. I'm going to take this to an x squared. I had 2x, so I'd have 2 times x squared divided by 2 minus the integral of cosine is sine x. And then I'd have my plus c, since I was an indefinite integral, no bounds on my integral. 2 over 2 will cancel and give me x squared minus sine x plus c. You can check, so this would be considered my original function. You can check out the derivative of this, of big F. The derivative of big F would give us 2x minus cosine x plus 0. So yes, this matches what I started with, so we are all good. Then here's the power rule, and you recognize the power rule. It says if I have a function raised to a power n, I'm going to increase that power by 1 in my antiderivative process, and then I'll divide by that same new power. The only thing I have to be careful of is that if n started as a -1 power, this rule does not work for that. It has its own rules, namely that it turns out to be the natural log function. Okay, so I'm going to use the power rule. I could think of that 5 being out front and increase my power. So I'd have x to the 8th divided by 8, add a c, and we'd have 5/8 x to the 8th plus c. Take the derivative of this, and you should get yourself right back to where we started. I like this problem. It is sometimes difficult for people to recognize. Maybe you could even ask yourself whose derivative is 1 over x, and you might say, oh, I recognize that. That is the natural log function whose derivative is 1 over x. So this turns out to be 3 natural log absolute value x plus c. Or we could have written this as x to the -1 dx, and then it follows this rule, which I cannot use a power rule for it because it is an antiderivative that results in natural log. For your reference, I've got the trig formulas, all their integrals are listed. And then we've got the logarithmic exponential formulas down below, just to bring those back to your memory bank, bring them out of memory. The a to the u one, it's a to the u over. We got to have that correcting factor of natural log a as a divisor. And then when log of a different base, it becomes natural log u over natural log a. And this one, I don't believe we've had to memorize that. So probably don't worry about that. I've not seen that on your AP exam. So I know we didn't use it in AB. Then we get into ones that are not quite as simple as the ones on the front side of the notes. This is where our U-sub kicks in. And we know that we have the chain rule. So if I had an outside function, it was the derivative of the outside, leave the inside alone, times the derivative of the inside. Well, U substitution works on undoing chain rules. So here was my original function, and somewhere present I need the derivative of a piece of that original function. So that's what I'm looking for, is an original function as well as a derivative present. That derivative piece is what we're going to set our u to be, and we'll integrate with respect to u. Then we can replace. I think once we get doing it, you will understand. So I'm looking for kind of that inner function g of x, and then I notice, so if I call this g of x, I notice that present is also g prime of x. I can see that e is a composite function. It's e raised to something a little more complex, like e to the x cubed. So I'm going to allow u to be the x cubed part, because the derivative, remember how we said it was du with respect to x, so it's du dx equals 3x squared. But I have dx here, so I'm going to make this du equals 3x squared dx, which was meaning really I multiplied both sides by dx and brought it up and over, giving me a du on one side, a 3x squared dx. We have done this work before, and we look to see what we have present. I have just x squared dx present, so I'm going to try and make a match for the x squared dx, which means I want to get rid of the 3, and I can do that by doing an inverse function of multiplying by 1/3. So that's going to be 1/3 times 3 canceling, giving us 1 there. X squared dx, a 1/3 du. And I am ready to do all my substitution now. So I have the integral. X squared dx is a 1/3 du. So I'm replacing those two pieces with 1/3 du. And then e to the x cubed gets replaced with just the u portion. And the integral of e to the u is e to the u. Since it's indefinite, it'll be plus c. And then I'm going to replace my u and swing back so that I have my variable with x's in it. And I look back here over to my u sub. U was equal to an x cubed. So there is our final answer. Next, I'm looking for the more complicated function, and my eye is drawn to this piece right here. I can see I've got a square root function as well as a 1 plus x squared function. So I've got an outer and an inner function. That inner function is like this g of x. So that typically is where you want to select your u. Notice that it does have a higher power than this right here. So I think this is a nice derivative relationship to get to x, isn't it? X squared will drop down to just x. May not be perfect, but I'm going to select my u to be 1 plus x squared. Let's just follow this through. Du dx, multiply up by dx, brings it to the other side. The derivative of my right-hand side would be 0 plus 2x. I have 6x, so I'm just going to make a match on this by simply multiplying both sides by a 3. So I'm going to multiply this side by 3, giving me 3 du equals 6x dx. And then we go into our substitution technique, and I'm going to say 6x gets replaced with 3 du, that coefficient can sit outside, and then I'd have the square root of u, because 1 plus x squared was my original u selection. Now, to integrate, I might prefer to write that radical as a rational exponent, and then it goes into power rule. Add 1 to the 1/2, that brings me to a 3/2. Dividing by 3/2 is like multiplying by 2/3, and then I'd have a plus c. 3 over 3 goes to 1. I have 2 u to the 3/2, but our u, I look back at my u substitution workspace, and I notice that u was 1 plus x squared. It is raised to the 3/2 plus c. There's our answer. Our original function would have started there, or the antiderivative is that. Oops, that looks like the same thing. Cotangent of theta. You may remember, because we did memorize this one, but if you don't remember, we can do it through u substitution. Let's rewrite cotan into cosine theta over sine theta d theta. And the derivative of cosine is negative sine, but also the derivative of sine gives me cosine. So which one do I want to allow to be my u? I'm going to allow the bottom to be my u, because this is a numerator response when I take my derivative, and that's what I want to match up to, is the numerator cosine theta d theta. Oh, that's a perfect match, isn't it? So let's go ahead and do u substitution. The integral of 1 over u, because remember sine theta was our u, and then cosine theta d theta is du. Sweet. This is a natural log one. If you don't recognize it, you might recognize it if you switched into exponent form. And that makes this natural log absolute value of u du. Rewrite that into x's, and my u, actually theta, sorry about that. My theta, my u was sine theta plus c. Final answer. Alrighty, sine cubed x. Yikes. This one looks tough, doesn't it? This one we've got to use some techniques that you probably, I don't know if we did in AB, but we will definitely be doing in BC. So we get a little bit more creative with this. I know that I can rewrite this into a sine squared x times a sine x. That would be equivalent to a sine cubed, correct? And like last time, when I took the derivative of sine theta, its derivative was cosine theta. So I feel like I need a cosine in this problem. And I can generate that by using Pythagorean identity sine squared x plus cosine squared x equals 1, which results in sine squared x equaling 1 minus cosine squared, just a little subtraction to bring cosine over to the right. So I'm going to use a replacement, not really a substitution, not a u substitution yet, but just a replacement for sine squared. I'm going to allow sine squared to be 1 minus cosine squared. Then I'll have sine x dx. We will get more practice with this particular problem or problems like it in the next section of chapter 7. So if this seems a little advanced, that's all right. We will be covering it soon. Alrighty, I think I want just to have cosine x be my u. I do that because I can see that if I take its derivative, I'm going to get negative sine x dx, which will work there, right? There's a match. Now, I don't need the negative though, so how about let's update this and say negative du is equal to sine x dx. Over onto our workspace, let's replace stuff. 1 minus cosine was u, and then it gets squared. So I'll have 1 minus u squared negative du, because we had negative du for sine x. Like I said, if this seems a little complicated, we will be hitting it again. Integrating 1 with respect to u would give us u minus u to the third, divide by 3, I'm going to say multiply by 1/3, plus c. That makes this negative u, but u is cosine, so negative cosine x. The negative distributes in and gives us a plus 1/3. U becomes cosine x, but don't forget the cubing. I'm going to put it right there, and then we have our plus c. And that is a rather complicated answer, one that you probably could not guess off the top of your head as the antiderivative of sine cubed. All right, last year we did these. Sometimes when we select our u, we don't get a replacement for everything. What happens then? So let's let u equal the more complicated 2x plus 1, because I see this as an inside-outside function. It's a composite function. Inside piece, square root being the outer piece. The derivative of this is not all that helpful for us. I am trying to match up to an x dx, but instead I don't get any x and I pick up a 2. So I'm going to switch and make this 1/2 on each side. At least I can replace the dx part. And you might say, well, then what are you going to do with the x? How do I get that replaced? Well, let's just kind of follow through here. We'll kind of have some mixed terms going on. I'm going to replace 2x plus 1 with my u. The square roots over it. Dx trades out to a 1/2 du, correct? And now I've got this intermixing going on of variables. That's not good. So, how do I fix that? Well, it just so happens that this becomes a very easy equation to solve for x. I can solve for x, it'll be in terms of u. So I have u equals 2x plus 1. So I will subtract 1 from each side. U minus 1 equals 2x. But I have just an x, so 1/2 u minus 1 is equivalent to an x. This becomes a substitution for us over here. So now we're going to replace x with the equivalent statement 1/2 u minus 1. Let's write the radical u as a rational exponent. And let's take this extra 1/2 out front so that we have just du there. This will give me 1/4. You're like, but I've got a multiplication. I know you do. But we can get rid of that. Let's kind of send it back to like a polynomial form. U to the first times u to the 1/2. We add those exponents, so that would be a 1.5. I'll call it a 3/2. Minus u to the 1/2 du. Oh, look at that. Now it's pretty easy to integrate, isn't it? 1/4 is going to stay outside. U, raise it by 1, will go to a 5/2, multiplied by a 2/5, minus u, increase your power, becomes 3/2, multiplied by the reciprocal 2/3, plus our c. And we can distribute the 1/4. 1/4 times 2/5 would be 2/20 or 1/10. Instead of u, oh gosh, I forgot what u was. U was 2x plus 1. Okay, so 2x plus 1, replacing that u, raised to the 5/2, minus, don't forget we're distributing to both of those, 1/4 times 2/3 makes 2/12. 2/12 reduces to 1/6. Replace the u, 2x plus 1, raised to the 3/2 plus c. Wow. Not extremely hard, but gets you a pretty complicated answer. And this is the ticket. We had that extra x, which we couldn't account for just in normal u substitution. It didn't come away from there. So then we just converted and said, okay, let's solve this for x and put it x in terms of u. And then it worked out quite nice. Lastly, a definite integral. Switch into a definite integral. So we're going to use u substitution. This being the higher power, its derivative would be something of an x form. So I like my chances for u substitution. Let's let u equal x squared minus 9. du is 2x dx. 1/2 du equals x dx. Awesome. It looks pretty clean, doesn't it? So we're going to have the integral x dx gets replaced with 1/2 du, and then x squared minus 9 was what we selected for u, so it becomes 1 over u. I'm going to update my bounds. Do you remember how to do that? So I know I have this relationship that u is equivalent to an x squared minus 9. So when x, how do I want to say that? When, not let, when x equals 0, u would equal 0 minus 9 or negative 9. When x equals 2, u is equal to 2 squared, so 4 minus 9 gives us negative 5. So when x was 0, u becomes negative 9. When x is 2, u becomes negative 5. And now I notice that I still have my smallest number on bottom, a bigger number on top, so I don't have to flip over and use that limit property of flipping. This will be perfectly fine. We can integrate on this. So 1/2 natural log absolute value of u, because that's the integral of 1 over u. No plus c on this. Rather, we have negative 9 to negative 5 as our bounds. And now remember, it's going to be f evaluated at negative 5 minus f evaluated at negative 9. Scrolling up here a bit, I am going to have 1/2. I'm going to pull my 1/2 way out front. Natural log absolute value of negative 5. Good thing that was there for the absolute value. Minus natural log absolute value of negative 9. Good that we had an absolute value going on. And let's just simplify this as much as possible. This would look like natural log of 5 minus natural log of 9. But remember, there's a property with natural logs. When you use subtraction, it can be pulled together into one natural log using division. First minus the second, or first divided by the second, so I get 5/9. Very nice. I'm curious because I can see one more thing that can be done. Oh, that's where the book left their answer as well. I was thinking, I could swing this back and make it a power, which would be a 1/2 power, and then I could actually kind of rewrite it into that, and then I could even simplify square root 9. But we've gotten far enough, I think. And finally, the last one. This is getting kind of lengthy. Let's let u equal. Oh, who's the derivative of what? Correct. Let u equal cotangent theta. The derivative of cotangent is negative cosecant squared theta. Haha, d theta. I like it. The only thing we got to adjust is the negative, so negative du is equal to positive cosecant squared theta d theta. Fantastic. Oh, and we got bounds work, huh? Do we really want to? I suppose we should. All right. When theta, hold it. Yes, that's right. When theta equals pi over 4, u will equal cotan pi over 4. At least that's it on a nice value, isn't it? That's like saying, no, it's not like saying that. It's like saying cosine pi over 4 over sine pi over 4, which is square root 2 over 2, which turns out to be 1. And it definitely is positive. Okay, what about when theta is equal to pi over 2? U would become cosine pi over 2 divided by sine pi over 2. That's like saying 0 divided by 1. We get a 0. All right, so we'll have to, I think we'll have some flipping to do here. Integral. Pi over 4 became 1. Pi over 2 evaluated to 0. Cotangent was our u, and this was a negative du. To follow all my substitutions. Pi over 4 shifts to 1. Pi over 2 shifts to 0. And then, oh, really, u was cotan. This was negative du. Well, this is easy integration at least. U to the second divided by 2, or 1/2 out front, evaluated from 1 to 0. Oh, I need to flip this, don't I? If I flip this, that is a negative property, so that negative will become a positive. Okay, so I'm going to shift this over into positive. If you'd rather see that done, you might want to write that. All right, 1 goes in, I get 1 squared is 1 over 2. 0 goes in, I get 0 halves. So final answer, 1/2. Sorry for the lengthy lecture today, but we covered a lot of ground. A little look at natural logs, a little look at some trig ones, and then of course just nicer ones. Your homework is on My Math Lab, and it is 7 2.A. Have a great day.